What you are looking at is the Fehmarnbelt, a stretch of sea nearly 18 kilometers wide, located on a major transport route connecting Scandinavia with Central Europe. To cross this gap, thousands of vehicles every day have to leave the road, wait to board a ferry, cross the sea, and then continue their journey on the other side. The sea crossing alone takes around 45 minutes. Or, if they choose not to take the ferry, they have to travel around the Great Belt, making the journey from Copenhagen to Hamburg nearly 500 kilometers long. That is why the Fehmarnbelt has long been a break in the transport route between Scandinavia and Central Europe. To remove this bottleneck, Denmark and Germany decided to create a fixed connection across the Fehmarnbelt. The final solution is a tunnel nearly 18 kilometers long, carrying both road and rail traffic. And this is also a project on a massive financial scale, with an approved financial framework of around 7.4 billion euros. When completed, the Fehmarnbelt will become the longest immersed tunnel in the world. But this is not a normal tunnel excavated by a TBM or built using drill and blast methods. At Fehmarnbelt, engineers are using the immersed tunnel method, where prefabricated concrete tunnel sections are placed into a trench prepared on the seabed. It sounds simple, but doing this across nearly 18 kilometers creates a series of major engineering challenges. How do you move these enormous structures out to sea, lower them into the correct position, and connect them underwater without letting water in? And why did this process become one of the most difficult parts of the entire project? That is what we are going to explore in today's video. And before we begin, don't forget to leave a like and give this video a boost, my friends. Now, let's get started. Before construction began, several options were considered for the Fehmarnbelt, including a bridge, a bored tunnel, and an immersed tunnel. The options were compared based on cost, technical risk, and environmental impact. A bridge could cross this stretch of sea, but the entire structure would remain above the water and be directly exposed to wind and weather throughout its operation. A bored tunnel, on the other hand, would require TBMs to excavate deep below the seabed. With the geological conditions at Fehmarnbelt, this option was considered more expensive and technically riskier. So the final choice was an immersed tunnel. The basic principle is completely different from a conventional excavated tunnel. Instead of boring a tunnel deep through the ground below the seabed, engineers create a trench along the route and place concrete tunnel sections inside it. These sections are then connected underwater to form one continuous tunnel. That means most of the tunnel structure has to be built before it is taken out to sea. And because of the size of the Fehmarnbelt Tunnel, these structures are far too large to be produced on a normal construction site. So a huge factory dedicated to producing tunnel elements was built on the Danish coast specifically for this project. And to understand how one of these tunnel sections is made, let's take a closer look at that factory. The factory is located at Rødbyhavn on the Danish coast, right next to the Fehmarnbelt. This is where the concrete structures that make up the entire underwater section of the tunnel are produced. In total, the Fehmarnbelt Tunnel requires 89 tunnel elements, including 79 standard elements and 10 special elements. Each standard element is enormous, around 217 meters long, 42 meters wide, and 9 meters high. Inside are 2 tubes for road traffic, 2 tubes for trains, and 1 technical tube running through the center. But a structure more than 200 meters long cannot be poured in one piece. So each standard element is divided into 9 segments, each around 24 meters long, and they are produced one after another on the same production line. The process begins with workers installing a dense network of steel reinforcement, creating the structural frame of the segment. Once the reinforcement is complete, the formwork is moved into position, and concrete is poured around the steel frame to create the tunnel structure. After the concrete reaches enough strength, the completed segment is pushed forward, freeing the production area for the next segment. A new reinforcement frame is installed, the formwork is closed, and more concrete is poured. And with every cycle, the tunnel element becomes around 24 meters longer. This continues until 9 segments form one standard element, 217 meters long. Once the concrete structure is complete, the element is left to cure for around 3 to 4 weeks so it can reach the required strength. From there, it is prepared to leave the production area. Both ends of the element are sealed with watertight steel bulkheads, while the ballast systems needed for transport and immersion are also installed. Sealing both ends is very important. That is because the element contains large, empty spaces inside. When water cannot enter, the air trapped inside provides enough buoyancy for this concrete structure, weighing tens of thousands of tons, to float on the water. The element then leaves the production area, passes through the basins in front of the factory, and moves toward the work harbor. These basins connect the factory directly to the harbor, allowing the enormous structures to be moved out to sea by water. But at this point, the tunnel element is only ready to go offshore. Before it can be lowered into its final position, the seabed of the Fehmarnbelt also has to be prepared. And that requires another operation on a similar scale, excavating a trench nearly 18 kilometers long along the seabed. To create this trench, dredging vessels removed around 15 million cubic meters of material from the seabed. The work is difficult because the geology beneath the Fehmarnbelt changes along the route, ranging from soft clay and hard limestone to large rocks left behind from the Ice Age. After nearly 3 years, dredging was completed in 2024. But the bottom of the trench still has to be flat and stable enough to support tunnel elements more than 200 meters long. So a special pontoon called Maya places a layer of gravel bedding along the bottom, creating a precise foundation for each element. Once the installation area is ready, the tunnel element waiting at the work harbor is prepared as well. 2 floating structures, IV1 and IV2, are attached to the 2 ends, while around 4,500 tons of ballast concrete are added to increase its weight. Tugboats then move the entire system out into the Fehmarnbelt and position it directly above the trench. There, water is gradually pumped into the ballast tanks, causing the element to slowly sink. Throughout the process, Ivy holds and adjusts the structure to maintain the correct direction, depth, and position until the element is placed precisely on the gravel bedding at the bottom. But this creates another question. How do you connect 2 tunnel elements underwater and keep the joint watertight? The answer comes from the pressure of the seawater itself. At the end of each element is a watertight gasket system. Once the new element is brought close to the one in front of it, the water trapped between the 2 ends is pumped out. As the pressure inside drops, the seawater pressure outside pushes the new element tightly against the previous one, compressing the gasket and creating a watertight connection. Once the connection is secured, gravel and protective rock are placed around the element. The same process is then repeated, element after element, until the tunnel stretches across the Fehmarnbelt. But before the first element could be lowered, the project ran into a problem with the most important equipment used in the process: IVY. IVY is a prototype designed specifically for the Fehmarnbelt project. The reason is that the tunnel elements here are much larger and heavier than those used for the Øresund tunnel, while the average working depth is around 30 meters, almost twice as deep as Øresund. This made IVY's mechanical and control systems more complicated than expected. Its construction, testing, and approval process took longer than planned, delaying the system by almost 2 years. And because no tunnel element could be lowered until IVY was ready, the delay directly affected the schedule of the entire project. Finally, on April 2, 2026, IVY passed its final tests and received approval from the Danish Maritime Authority. Just over a month later, on the evening of May 4th, the first tunnel element left the work harbor and was taken to the installation site by 5 tugboats. The immersion process then took around 14 hours before the 217-meter-long structure was placed precisely into the trench in front of the Danish tunnel portal. For the first time, a real section of the Fehmarnbelt Tunnel was now lying beneath the seabed. After the first element, the immersion process continued along the Fehmarnbelt. By early August 2026, the first 3 tunnel elements had been successfully placed beneath the seabed. But even after the concrete tunnel structure is fully connected, the project will still not be finished. Inside the tunnel, crews still have to install the roads, railway tracks, as well as electrical systems, ventilation, drainage, fire protection, and safety systems before the tunnel can begin operating. The Fehmarnbelt Tunnel was originally expected to open in 2029, but construction delays have forced that schedule to be revised. Under the current plan, the road connection will open first, followed by the railway, once the related infrastructure on the German side is completed. The new opening schedule is still being updated. Once the tunnel enters service, crossing the Fehmarnbelt is expected to take around 10 minutes by car and 7 minutes by train. More importantly, vehicles will no longer have to stop in the middle of their journey and wait for a ferry. The Fehmarnbelt will become a fixed road and rail connection between Denmark and Germany, shortening the transport route between Scandinavia and Central Europe. And that is the final goal of the project, to remove a bottleneck on the sea by building a transport route directly beneath it. That brings us to the end of today's video. Thank you for staying with us all the way to the end. If you enjoyed the video and found it useful, don't forget to leave a like and give this video a boost, my friends. For now, goodbye, and I'll see you again in the next video.